Today we're going to start looking into a theorem that's probably going to take us a couple days to go through. That is the poincare-birkoff-witt theorem. I mean, I don't know exactly how long it'll take us, but it's going to be at least a couple of videos worth. So, the first theorem we mention here, we set up as so. I guess I should number these as they do, in case we need to reference them. So we're going to let G be a Lie K-algebra, U its enveloping algebra, G the graded algebra, of U, and S the symmetric algebra of G as a K module. If G is a free K module, the canonical homomorphism omega from the symmetric algebra S to the graded algebra G is an isomorphism. And also, I'm pretty sure we're gonna have a bunch of like setup theorems first, so I'm pretty sure this is just one of those. We're going to let x lambda indexed over big lambda be a basis of the K module version of G. With a total ordering of big lambda. Going to let P be the polynomial algebra K over indeterminates Z lambda for lambda across our indexing set, with a Z lambda for each x lambda, and vice versa. For every sequence M of indices from big lambda, so these are elements of our indexing set. We're going to let Zm be their product of the associated indeterminates, and Xm be the tensor product constructed in the same way. Where is my, there we go. All of these Zm for increasing m, so we don't, just so we don't double count any by like permutation. Form a basis for our polynomial algebra as a k-module. With the empty set being a sequence and the empty product being 1. Now, we're going to let the PP and P be the submodule of polynomials of degree at most p. So we need some limits. So, and we write that lambda is less than or equal to a sequence m if lambda is less than or equal to mu for all mu in the sequence m. So, lemma 1. For every natural p that is natural numbers with 0, there exists a unique homomorphism Fp of the k-module of the tensor product of the k-tensor product of G with the polynomials of degree p into p is a k-module such that it satisfies some conditions. We're going to call this one, first condition we're going to call AP. So that Fp of the tensor product of x lambda with Zm is equal to Z lambda Zm for all lambda less than or equal to m, and Zm being of degree at most p. BP is that Fp of x lambda tensor Z to a sequence minus Z lambda Zm is going to be inside of PQ, and this is for Zm in PQ, where Q is at most P. So in this case, unlike the above, z lambda isn't necessarily a member of the sequence defining zm, but the image of their tensor under fp is still essentially equivalent to z lambda minus zm mod pq in the way that, you know, I mean. And our third and final condition here, CP, is that fp of x lambda tensored with fp of x mu with z of a sequence n essentially gives you fp of x mu tensored with fp of x lambda tensor zn. So in this case, those two elements swap, plus our second term, which is fp of the bracket of these elements x with tensor product of the result of that with zn. And this is for zn in p to the p minus 1. And keep in mind, this all lines up to be in the domains you need to because of this condition given by BP. Oh, and there is in fact one more which they don't label. I'm going to call it DP. The restriction of FP, the tensor of G with P to the P minus 1, P of P minus 1, gives you the previous F. So dp is implied by the others. As the restriction will satisfy, if I can learn how to spell that, the previous versions of the conditions, which is why we have them indexed by P. Now we need to prove existence and uniqueness, and as always we're going to be getting that, as you can imagine, through induction. We will be getting existence, uniqueness through induction. Because keep in mind, F, we don't have a map F that we want to show has these properties. We want to show that we can build a map F. So our base case is P equals 0. In that case, A of 0 states that F of 0 of x lambda with the tensor of, well, we saw that the Z of the only possible sequence we have of 0 elements is the empty set, and Z empty is just going to be 1. And this is going to be sent to, on the right we can see Z lambda with Zm likewise being 1 as an empty product. Alright, and then so B0 and C0 fall from that pretty directly. And B0 says that F0 of X lambda tensor 1 minus Z lambda is in P1, which means it has order of 1, which I mean is obviously going to hold true. And working through C seems like too much work, but it's very similar, as you can imagine. Now, inductive. The inductive case, we're going to assume that we have after the P minus 1 as desired. So, and we want to extend this to our next order of polynomials. One more. So we need to show P minus 1 has a unique extension to a unique extension, we're going to call it FP, and that is going to be the k-tensor of G to the polynomials of P terms meeting the conditions. First, we need to define FP of X lambda tensor Zm for our new M, because M is going to have one more term than we had before, remember, because it's going to be in increasing sequence of P terms. If lambda is less than or equal to M, then we have from condition AP the FP X lambda tensor Zm is equal to just Z lambda Zm. Easy enough. Otherwise, we write M as the composition of mu and n where mu is less than lambda and mu is less than or equal to n. So essentially we're just dropping out the lowest term, which means it is unique, obviously. And this gives us the constraint that Zm is equal to Z of the lowest term from M times Z without its lowest term, which is equal to F to the P minus 1 of X mu tensor Zn by a to the p minus 1. And this gives us the left-hand side of condition C. Keep in mind, this is going, FP has to act the same as its restriction by D. So this gives us our left-hand side. Now, by b to the p minus 1, we have a new condition. I'm going to try to keep as much of this on screen to make it easier to follow. This gives us our condition that f to the p x lambda times zn is through, we get this through D that this is minus 1 because it's in the lower area. And this we can then write as z lambda zn, and then keep in mind that this difference between these two terms from before has to be inside what we called their PQ. So we're going to have this condition for some w inside p to the p minus 1. And this gives us the right-hand side. Keep in mind with swapping the order and then adding that with the Lie bracket of the z's. So that's going to give us as z lambda, z mu, zn. So f to the p minus 1 x mu tensor with this w plus f to the p minus 1 the tensor of x lambda x mu with z of this series n. So plugging this into the left-hand side of C and this into the right, this defines Fp uniquely through a formula. Satisfies AP and BP. Now keep in mind we designed this around also assessing CP, but only under the conditions that mu is less than lambda and less than or equal to our sequence n. This condition is trivial when mu is equal to lambda and so is satisfied when we have lambda is less than n or mu is less than n. So the only case we have left is if none of these hold. We can write n as VQ. Once again, we peel off a lowest element. V less than or equal to Q. It is less than lambda. It is less than mu, and that actually might be a nu and not a V. I'm going to be abbreviating the image of under FP of X tensor Z as X, not times Y, Y is nothing, XZ. For X and G and Z polynomial of order P, we have, by the induction hypothesis, an X mu Z Dn is equal to X mu X nu Z to the Q, which is the peeled off version of N, which gives us X nu times X mu Z Q plus their bracket, which is X mu X nu, and then times ZQ. Right. Now we see that Z mu ZQ is equal to Z mu ZQ. I'm writing the subscripts too small. Plus mu plus W, where W is 0, which is inside of P to the P minus 2. So condition CP can be applied to X lambda of X mu of Z mu ZQ. Since mu is below Q and also below mu, and nu is below mu directly, and also see this can be applied to X lambda of X mu times W by the induction hypothesis, and so to X lambda X mu ZQ. Hence we can finally crunch this all down into X lambda X mu Zn equal X nu X lambda X mu times ZQ plus the bracket of X lambda X mu ZQ. This is going to be a bunch of terms here. mu comma x nu x lambda zq plus the bracket of x lambda with the bracket of x mu x nu times zq. What a mess. Now, there's one more step to go. Exchanging mu, lambda plus mu, and subtracting. We get a whole big mess. Lambda zn, what is this going to give us? We have x nu times lambda times x mu zq minus swapping x mu and x lambda plus x lambda with x mu and x nu zq minus x mu with so many x's, dude. X lambda, x nu, zq, and this we can show is we see is equal to xv of the bracket of x lambda x mu zq plus x lambda with x mu x nu zq plus x mu, the bracket of x nu and x lambda zq, and this all crunches down kind of into the bracket of x lambda x mu of the product x nu and zq plus what I'm going to write as the Jacobi triple of x lambda x mu x nu times zq, capital Q of course, and so that is going to disappear on the right. So this here is going to turn back into Zn, and this whole thing by the Jacobi triple is going to turn into 0. And we are finally done. Thank God. Alright, so we've got another lemma here, not nearly as painful. Let's take a look at it here. Lemma 2 exists a map sigma from G into Lk of P, which is an alpha mapping, such that first condition is that sigma of x lambda Zm is equal to z lambda Zm for lambda less than or equal to m. Condition 2 is that this same term on the left is congruent to the same term on the right. Mod polynomials of P with P order f, the order of m is P, that is m has P elements. And the proof of this is going to be much shorter. From lemma 1, exists homomorphism of f of the k tensor of G with the polynomials of order P into P with the given constraint, with the constraints A, B, and C we saw before. The constraints we saw before. I'm not writing them all out again. This homomorphism defines a new homomorphism, which we're going to conveniently call sigma, of G into Lk of P and this sigma is an alpha mapping from condition C. And properties 1 and 2 just correspond to conditions AP and BP. And that's all we actually need to do. And we're done. Okay. I think we'll do one more lemma here, and then we'll end it with that. Going to be our third and final lemma of the day. We're going to let T be a tensor in the intersection of Tn with J. The homogeneous component Tn of T of order n is in the kernel, which we're going to call I, of the canonical homomorphism from the tensor algebra to the symmetric algebra. So we will write this component Tn as the sum. So the index is going to go from 1 to r of x, sequence i's, where mi are sequences of order n inside of r, lambda. Then sigma extends to a homomorphism from T into the algebra Lk of P. And we'll just write sigma again. Just going to overload it. Is 0 on J. For lemma 2, the image of T as a whole under sigma, acting on 1, is a polynomial whose terms of highest degree are these z, mi, indexing I as before. Now, as T is in J, we saw before that this extension of sigma is 0 on J. So the sum of R, which we can write image as, has to equal 0 in P. Now, P is canonically identified with S since G has a basis of Rx lambda for lambda in big lambda. Hence, the canonical image of our Tn and S is 0. So we can't get any cancellation on the other side. And that's the same thing saying that Tn is in the kernel. Now, do we, yeah, I'll write one more little note and then we will end it here. So we have what we need now, finally, to prove theorem 1. We need that the canonical homomorphism of the symmetric algebra onto the graded algebra to be injective. That if we have a T, a tensor of M, and C from T onto U is the canonical homomorphism, as it always is. So that we need to show that C of T is in some UN minus 1, then T is in the kernel of this homomorphism. Sorry, my chair. Now this condition we have of CT being in U minus n minus 1 means there exists a tensor T prime from T to the n minus 1 such that the T is equivalent to T prime, essentially mod J. And this tensor, that is T minus T prime, admits T as a homogeneous component of order n. Just keep in mind T is in T superscript n and T prime is in T subscript n minus 1. And hence T is in the kernel by our previous lemma. And that is the proof of the first theorem, I believe. We have more corollaries than that, but we will be doing that next time, I believe. Yeah, we've done enough. That's the end of math. Oh, we have done enough.